Good afternoon, guys. How many people feel sleepy?
You're feeling cold.
Feeling cold? Okay, got you. Okay, so my name is Vince Kohli, the host for Room 209. I'm pleasure and delighted to introduce SK. SK has been coming to these conferences so often. He's a remarkable speaker and very impactful, a very beautiful storyteller. So I would love to make a quick introduction. So I'm a judge at MIT. Basically, handle a lot of startups in blockchain and cryptocurrency, and also invented a new program in Silicon Valley is called problem thinking. The idea is why fail fast when you can fail exponential. But here the show belongs to SK. SK, with great honor and respect, please.
Thank you. Thank you. Thank you, everyone, for coming. I'm going to be recording my session, but I'll be only recording myself, not you guys. Anything after lunch, it's always a difficult situation, talking and keeping you engaged. I remember a few years ago when I asked a professor, how do I make sure that the audience are engaged? I said, just make sure you're telling some nice stories and watch the body language. As long as they're engaged, you can see them changing the facial expressions, and if you walk up and down, you can actually see the eyes moving left and right. But if they're not engaged anymore, that means maybe the pens are down, the computers are down, even though they have trained their eyes to move up and down along when you walk, but they're really disengaged, and that's the time when you stop. What if I still have content to share and they're disengaged? I said, then bring them back to engagement and you can tell them a story. I said, okay, fine. But let me start with a story. You guys like stories? Yeah, yes, yeah. Now I come from India, and normally when we say yes, we normally do this, and we say no, we do this. So do you like stories?
Yes.
Okay, fantastic, yeah. I'm going to actually talk about the practical implementation solutions of certain smart city use cases using deep learning techniques. I will talk at a very broad level first to talk about some of the smart cities and the infrastructure and the architectural needs of it, but then I'll pick a few use cases to explain more specifically how applying deep learning techniques you can solve the use case more efficiently than, let's say, even 6 months ago, 1 year ago, using machine learning, or maybe non-AI techniques being used, I think, a year ago. And in that process, I may even make a few predictions. And when I talk about predictions, I was sharing this story during lunchtime with a gentleman. There's a professor by the name of Philip Tetlock who did a research between 1983 to 2000 for almost 20 years. He tracked all the so-called experts to figure out all the predictions they are making, are they coming true or not? So he tracked 284 experts, around 28,000 predictions made over a period of 20 years. And the summary, he actually wrote a book, and then it was New York Times bestseller too. The summary is, the more expert you are, the less accurate your predictions are. With that story, I'm actually going to make a few predictions too. Take it with a pinch of salt, and then we'll go with that. So this is about me. The traditional use cases, there are so many use cases about smart cities. The parking lots, or identifying where the theft is happening, or trying to find out which roads are being overused, and how to manage traffic congestion. There are so many use cases, but there are certain use cases that can be still solved using smart city solutions, which are not so popular. For example, in New Orleans, they are using a smart city solution to identify where there is a higher probability of fire. If you have older buildings and the propensity for people not taking enough precautions, and hence by the city to invest more money in those areas to prevent fire, destruction, and death too. So that's another use case which is not very commonly heard of. There's another fantastic use case where in certain cities, especially very congested, densely populated cities, the city government has to make regular inspections of restaurants. And if you want to find out which restaurants need to be inspected more frequently, you can actually use a smart city solution. And there's another practical implementation of it, though not a deep learning technique used in this context, even though it's a machine learning technique, but it's a very common problem you may see. A year ago, I wrote a blog about how to be innovative and how to be creative. One of the simple tests of finding an opportunity where we need to find a solution for this is, it's called curse test. Curse, actually cursing. If you find someone cursing, yeah, I want to find this solution for this. Oh my God, this is so bothering me. That's an area you want to be focusing on. And this is one of the common problems apparently for city governments, to find out which restaurants are following meticulously regulations which are not, and hence need more regulation and more inspections. Cities have congestion and cities have a pollution. To find out which areas are lots more polluted and may be affecting the health, this is a sensor-equipped asthma inhalers in Louisville, to find out which areas in the cities and what times of the day, what times of the year or the week you got to pay more attention for to make sure there's a little more clean air provided. Now, these are all use cases which I would recommend, in addition to the regular use cases I talked about. So these are some of the simple list of use cases. I'm actually going to pick a few which are on the bolded text. I'm going to talk about those. But I will actually show the implementation details of these use cases. Now, in my current job and a previous job, we developed a few platforms, actually a couple of platforms, smart city solutions, to address the aspect of how to get the data, how to store the data, how to process the data, how to keep the data ready for future processing, and final but not the least important, of processing the data to address a problem statement. These are some of the use cases we solved using the platform. But because I cannot reveal the platform details of the company, I'm actually going to be sharing with you some very popular technical papers published which were inspiration for us to develop the platform. Maybe you can take some clues away from those papers. Every time I refer to a paper, I would show the link of that paper at the bottom of the screen so you can take a picture. Going back to the professor who told me how to keep people engaged, he said, make sure you give a task to the people every 5 minutes they can do something. So I want you to take up your cell phone and take a picture of the screen if you want to know the link of where I got the information from. And I'll pick a few of the use cases. If you have any questions, of course, you can let me know too.
Going back to this one, restaurant case, what kind of data sets they're looking at?
Actually, that is a very good question. If you see, there were only 11 variables used. And I mentioned those things too. And you can actually find more information at this link provided here. But this is not a deep learning solution. They actually used a regular machine learning technique where they just got a few features, in this case 11 features, and made a prediction. It's more of just a classification, yes or no. Someone needs more inspections, someone needs no additional inspections, and then you find what it is. But the point I'm trying to make in this slide is there are so many non-commonly heard use cases that need to be solved are also being addressed using smart city solutions. Going back to this, one of the first, if you are a company trying to develop a smart city solution, or if you are an individual trying to develop a smart city a platform or a product or a solution on yourself, the first thing you got to work on is, what is the amount of data I'm getting in, and how do I even conceive of the infrastructure to process the data or to receive the data? This is a macro level various modules provided that will identify first the various types of data sources which you will be getting. And remember, the data sources can be today your cars or mobile devices or your sensors or your personal devices, what you're using. But there could be more devices coming in future, maybe the street lamps, or maybe certain other vehicles that are going to be drones, maybe they're going to be, or even cameras may have their own sensors which will be sending data for the central processing unit, and hence you got to be aware of the current and the future data sources. Next is, what type of data collection methods are you using? What are the various standards would you be using, and how are you going to make sure the product is going to be in future scalable and also will support newer types of products and newer types of data standards that's coming in. if I do a broad dissection of the entire infrastructure, you would talk about some sort of a data coming in, storing in, queuing it, messaging it, all of that information. And the messaging and queuing can be if you have a separate agents or engines running, processing the streaming data, or intermittent data, or a short-term usable data, or a long-term usable data, or let's say numeric, text, audio, video, and also even signal data. Talking about signals, you may know this, but I'll tell you a very exciting research going on in the world now. It's not widespread research yet. I've seen papers being published only in the last 1 or 2 years. And the papers are only from the academic circles. A few companies are working on this, but they have not released it yet, is human activity detection. For example, if someone is walking, running, falling, getting shot, or accident, this human activity detection has been predominantly done in the last 1.5 years or 2 years using video. So you actually have a video camera, it's actually video feed coming in, and then this model which is evaluating the video and then figuring out what's happening. But the problem in the process, there are 3 problems. Number 1 is a privacy concern. People don't want their pictures being taken, whether it's an airport or a hospital or a stadium. They don't want pictures to be taken, but you want the video feed to track what's happening. Number 2, the lighting. Sometimes, let's say if you are doing a patient tracking and a patient is sleeping in the night, you turn off the lights and sleep. And the model cannot see what's happening. Let's say the patient is going through a cardiac arrest or cannot breathe, or maybe tossing and turning, which needs medical attention, but the model cannot figure out because it's dark. Third problem is something called line of sight situation. The patient has to be in the visible sight of the camera. What if the camera is there? Even though you can set up a camera which will focus on the entire building, but what if a patient is right next to the wall there where the camera cannot even see? As a new research which is using Wi-Fi routers, the router signals being used to detect human activity. So you don't need to use cameras anymore or videos anymore, but you can actually use router signals. So you actually have a router right there, and many, of course this works only in the indoor situations. In any indoor, whether it's a massive stadium or a small conference room or a theater, movie theater, or a hospital, you can track the human activity. And the human activity is not just standing, sitting, falling down stuff, but even some of the subtle activities like breathing or even typing. There is a paper published which actually figures out what key you are typing. Of course, the accuracy rates for certain keys is higher and the accuracy rates for the certain other keys are lower. And if the router is even in the next room, as long as you're able to get the signals in this room. So for example, if you're typing something, I can find out what you're typing. So you got to be careful about that, what you're typing. The point I'm trying to make is, in this data processing infrastructure, you have to be aware of the types of data, the variety of data that comes in. So numeric, text, audio, video, signal, and all of the data too. Another, even though I talked about numeric data, video data, image data, I really wanted to have a special slide on just the text processing, because text is a weird animal when it comes to AI. Let's say you're doing a machine learning solution or a deep learning solution for numeric data. You want to predict the stock price of a company ABC, or you want to predict when it's going to rain, or you want to predict when there's going to be a terrorist activity or whatever. You can use a lot of numbers and process and do a deep learning or a machine learning technique on that. But text, how do you do that? There's a lot of pre-processing that need to be done for text processing. And this is, if you're developing a platform, you got to make sure some of these pre-processing ideas are already taken care of. Lowercasing, lemmatizing, stemmatizing, tokenizing, all of trying to breaking up sentences, paragraphs, and even words into smaller pieces that make sense. And sometimes an individual word has to co-occur with a couple of other words, and the model has to figure out what it is. United States of America is a single word because it actually all 4 words go together. So the model has to figure out, and that type of pre-processing also need to be done. So going back to my initial comment, if you're working for a company which is developing a smart city solutions, the initial framework of how to make sure you capture all the data, but special attention to be paid towards the text processing and text storing information. And how about the infrastructure? Again, this is another very, very a simpler view of what the infrastructure is going to look like in a smart city. And again, there's according to United Nations report in 2011, I think, the number of cities with at least 5 million to 10 million people in a single city is going to go up to 30 to 50 cities in the world. 50 cities, at least in this world, will have 5 to 10 million people. Just to give a context, Finland, I think the whole population of Finland is, I think, 6 million people. I think whole population of Sweden, maybe I think it's around 9 million people. So if you're talking about cities, just a city in a small country, in a country having 5 to 10 million people, it's a massive thing, and that too, it's quite a dense activity, and people have to pay attention to that. And this is an infrastructure architecture. Again, for more information, you can read this paper. By the way, all the papers I'm going to be sharing today are published in 2017, or a couple of papers in 2018. Which year are we in? 2018. So this is not an ancient technology or research. I'm talking about 2017 research. And to read, even if you know archive.org, the way you read a number is, this is the year of publish, the first 2 digits, and the second 2 digits is the month of publication. So it says 2017 March published, and that's the serial number of the paper. So in this, you talk about various types of sensors, whether it's your traffic lights, vehicles, individuals, mobile devices, drones, airplanes, whatever it is. I think they have so many and personal carrier devices. And you collect the data, and you actually have lots and lots of servers correcting the data. And of course, you go to a little bit of a load balancing to make sure you don't lose any of the data. You got to understand which data is of short-term importance and does not have a long-term benefit. For example, at 9 a.m., how much was the rainfall, and 9:30 a.m., how much was the rainfall? That information is required one maybe for a short term, but that information as a compiled version of the hourly, half a day, daily, total rainfall may be useful for a longer term benefit, but you don't need, after a year, how much was the rain at 9:30 a.m. on the 2nd of April. So the short term benefit, long term benefit, I think need to be looked at, and also you got to understand, when you have the mainstream collects the entire amount of data, and some of that actually will be given off to third parties for maybe providing APIs, and so you actually have a public stream. And then you actually store for long term, do a little bit of processing. One aspect which is not highlighted in the slide in this context is the privacy of the data. Let's say if you're a smart city and you're providing medical services to your patients, and you are, let's say you have given an mobile app to all of your citizens, and then if someone is going through, let's say, a cardiac arrest or have a medical problem, and then the person is unconscious, not able to speak, and when the paramedics come in, they would want to know what is the condition you have currently and the previous condition, and then what need to be administered and cannot be administered. They have to have access to your medical records. But at the same time, you don't want unauthorized people having access to your medical records, and hence privacy will become another complication too. Of course, we have GDPR in Europe, but I think we are waiting for a similar thing happening in the United States too. Oh, by the way, if you're looking for a fantastic job opportunity going forward, there is still, I think, relatively unknown, but in the next 6 months, there's going to be a tremendous number of jobs, is GDPR analyst, just offering consulting services to tell whether this project complies with GDPR regulations or not. It will be a huge, huge expectation for many, many multinational companies. If you remember SOX compliance, I think 10 years ago, there was such a huge consulting opportunity for companies offering SOX advisory. Now there'll be a GDPR advisory coming. So if you guys want to pick up something on GDPR, will be a nice thing. Okay, now comes the deep learning part of how some of the use cases. So I'll talk about some of the use cases using video processing. I do understand the privacy concerns, and I do understand the darkness and the line of sight situations, but I think video is going to be there for at least a few more years, helping cities and governments companies process information and make sense out of the whole process. a few of the use cases are, the two most important, most commonly used use cases are person re-identification and vehicle re-identification. You actually want a person to be re-identified or identified, or a vehicle to be identified, and that's going to be a huge issue. But I will talk about that in a minute about a specific use case from a paper. But in a video, let's say if you have 1,000 cameras in a city, which actually is a very small number. Typically you have 10,000 to even 100,000 cameras. I think in one of the big Chinese cities, they're even having 100,000 cameras in the whole city. So every 1 hour, how many hours of video are you getting in? 100,000 hours of video is getting in. Maybe 99% of the video is going to be just useless because you're going to eventually throw away, but you just can't throw away immediately. You got to keep it for some time. What would be the some time? You got to figure out. And if you're going to store it in a single central location, then you have a single point of failure. If you have distributed, then you actually have an expensive infrastructure. Here, maybe I think you should read this paper a little more, just published 4 months ago, about how to make sure the video that's coming in, that's even transmitted on the network without impacting the bandwidth of the network itself. So you actually can compress the video first and then from the edge device and send it off to the central server. Or there is a couple of papers published in the recent past about how do you have the edge devices process some of the video and send only some of the salient features or salient information for central storage. That's 6 months ago I wrote a blog on how to move existing image processing models into mobile devices. If you have AlexNet, ImageNet, ResNet, there's so many image processing models available which actually have millions of parameters and gigabytes of data memory takes for processing, and even not so quick response time, maybe second, maybe less than a second, but I think it's still, 1 second is still a huge time. Except model like YOLO 2 or YOLO 3, which actually takes maybe 20, 50 milliseconds for processing. These models all exist in the cloud, and hence you don't have a limitation on the computing and the storage capacity. But what if you want a drone or a surveillance camera or your cell phone or your laptop to process some of these videos that's coming in? You need to have these models located on these, and if it's a cell phone, if it's a drone, you have limited storage, limited computing, limited power supply, and hence you got to balance between the number of parameters and amount of computing energy it's going to take versus the accuracy. Currently, all the models that are being deployed in mobile devices have a lesser accuracy because they're sacrificing the accuracy for the benefit of response time and the computing time. Excuse me. So in this process, the paper actually talks about earlier, maybe 1 year ago, there are codec standards which were proposed on how to compress and transmit the compressed video to the central storage space and then for further processing. You actually can do a feature extraction, and you got to figure out what type of features you want to extract, which I said even earlier, salient features. Get the salient features out of the system and store it in your central system. Okay, this is one of the very simple use case, counting the number of cars in a parking lot. Now, what's the benefit of doing it? Without naming a company, we developed a pre-processing platform for a San Francisco-based company. They have around 150 to 200 satellites in the sky. They are taking pictures of Earth every day, and they are taking 500,000 pictures per day of the entire Earth. Each picture is of almost 2.2K pixels by 2.2K pixels size. One of the use case this company found was many retail companies, in addition to their own predictions, big data solutions they have to predict what will be the sales in the next 1 month or 1 quarter, they wanted to use some additional techniques to make a little more accurate predictions on how much is going to be my sales going forward. Marketing came out and said, you know what, can we count the number of cars that's being parked in our parking lots? Of course, that was the first use case. Eventually, they want to find out number of cars plus the duration they were parked for. But we'll not talk about the duration right now. Just to count the number of cars parked. The additional use cases was the types of cars, whether it's a 2-door or a 4-door or a minivan or a thing, which actually would signify what type of customer you are, and then the color of the car also would make an impact on in terms of the buying decisions and stuff. But that would be one use case, identifying the number of cars in the parking lot. So there are two examples I picked up. There's two papers I'm sharing. YOLO 1, YOLO 2, YOLO 3. YOLO 3 is the latest one. YOLO stands for you only look once. It's a model, image processing model, which processes a video frame by frame and identifies objects in it. The first YOLO 1 came out, I think, a year and a half ago. YOLO 2 came, I think, almost 10 months ago maybe, and YOLO 3 came a few months ago. YOLO 1 was slow in the sense it takes a second and a half to process. Let's say if you install the YOLO onto your mobile device and you hold it up against, let's say, on a street, it starts identifying people, cars, plants, street lights, all of that stuff. YOLO 2 came out and they actually made it so fast, it actually became 40 frames per second. So it's almost real time. So it actually can be put on the autonomous cars too. YOLO 1 cannot be put on autonomous cars because if it's taking 1 second time to detect what's happening, then within a second your car will be driving 50 to 60 meters, even 100 meters, and then you actually have a problem. YOLO 3, which is just recently published, I think you should all go check the website. This is, of course, the paper published by them in 2015. But YOLO3.org or .com, I think is the name of the website, or just say YOLO V3 and you'll find out more information about them. It's so fast. They have ported it to mobile devices too. By sacrificing a little bit of accuracy, you get really, really fast YOLO 1. So it actually finds out the object. So if you have a smart city solution to be implemented, you want to find out, let's say 10 classes, maybe dogs, cats, people, cars, bicycles, I don't know, maybe 50 classes, maybe 100 classes you want to find out and make a classification model, you can use YOLO. Or there's another paper published where it actually identifies the pixels. This is the beauty of deep learning. It identifies which pixel in an image represent a car, because at a very high elevation, a car could be actually identified by a pixel or maybe a couple of pixels in the neighborhood. So it draws a rectangle around the central pixel, and if you train it effectively, it will identify all the cars and will not pick any of the rooftops, even though they look almost like a car. See, the picture is actually vague because you can't actually have a very clear high image, high fidelity picture. So you actually can detect the number of cars. Now I have a implementation of the traffic flow solution, which is not a high-tech. Here is a paper published again. We have used this paper as an inspiration. Using radio signals, you actually can have 2 or 3 radio transmitters and receivers on both ends of the road, and you can actually track, and the logic being when the transmission gets interrupted, that's when you know the car is going, and then you can do a classification of the car. This actually model was used to figure out how many cars and what types of cars. So not just counting the count of the cars, but also classification of the cars too. So is it a small car or a big car or a truck or a bus? I think they have 4 or 5 classes it can figure out. Now what's the use case for this? Of course, is just to predict which roads which areas have traffic congestion, and then you can make an accurate prediction. You can get a temporal information and then figure out what needs to be done, maybe road widening or road diverting the traffic, whatever. But another use case in the process is if you have certain roads being overused, you can use the same model to figure out which roads need relaying more frequently than the other roads. And hence, this would be a very, very simple technique. So, by the way, in the traffic flow detection, unlike in the previous, some of the other use cases, not only you have to care for a longer term, the devices have to work on a longer term, but also be resistant to weather conditions, like there's rain or heavy wind or dust, the models still have to work. In this case, with the camera, I think they get blocked because of the dust and water. Here, the reader signals don't get affected as much. So that's another implementation, practical implementation detail that need to be paid attention to. But if you are a software engineer trying to develop only the smart city solution on the system, you can ignore that part. But you've got to be aware of that possibility of devices getting corrupt and then not able to give you correct data, and then hence your model is going to become problematic.
Can I ask you a quick question? Similar to traffic flow detection, can you, elaborate this, evolve this model into wind detection, wildfire detection, earthquake detections? Because that's some of the risk management issues a city always has.
Yeah. The answer is simple answer is yes, but I think the signals or the input data you're going to take is going to be different, quite different. In this case, the signal you're getting is the radio signal transmitted and received. So you have a transmitter on one side and the receiver on the other side. Whenever there's an interruption of the signal, then that's when it is. And if you have multiple transmitters, let's say at a distance of let's say 1 meter or 2 meters, the longevity of the interruption would give an indication of the size of the car or the vehicle and stuff. But if it's a wind and other things, you got to have different inputs. But I guess the underlying machine learning feature extraction and the classification model could be very similar. Yeah. Okay. What time? 1:40, right? So I'll try to finish it fast. I do have a few other solutions too, but if you have any questions, please interrupt me. Face recognition and vehicle recognition is one of the most interesting problem statement. I think I want to really explain that to you guys, why it's interesting. Let's say you have a Facebook account and then you post your picture, or let's say you post your friends' pictures. Because Facebook already knows your friends or you, it can easily detect, okay, this is Mr. ABC or Miss ABC, and it can detect. But in a smart city solution, privacy of course prevents, but otherwise also you can't have the pictures of all the people in the city, and hence if some new incident happens, I want to find out who the person is, you don't have an existing database. You can find out, let's say, is the person I saw in camera 123 in city part A at 9 a.m. on Sunday, is it the same person at 3 p.m. on a Tuesday in the other part of the city? And the first picture, I can see a front image, and the second image, actually, I can see a side angle. It was late or night or dark, not with clear visibility. How would you match these two pictures? And then, of course, you will still do a background check to find out who the person is. But if you want to find the matching, that's going to be hugely impossible task. If you have, let's say, 1 million people, if you want to do really one-to-one matching, it is million times million combination of activities. You got to do comparisons. It's almost impossible just for 1 million. And if you're talking about 5 million people, I think 5 million times 5 million is almost impossible to compute. Here is a solution. Again, more information. I think you can find the paper there. In this, they actually have two types of scenarios. The data set can be open data set and a closed data set. Closed data set is, what if you already have the pictures of some people of interest? Whatever reason it is, you actually have people. And the model is, it's very easy for the model to compare against that, because whenever you get a picture from any particular video and you have an existing database, that's a closed set and you actually can compare it against. If you have an open set, that becomes an extremely complicated problem, because you don't have, that is, the model has never seen the picture of this person. So in this paper, you see there's they have run multiple tests using just the basic softmax loss and how accurate the model was. And there's something called triplet loss. Triplet loss is, you want to find who this person is. So let's say xi. You look at another image xj, which is very similar to this person, and xk, a third image, who's distinctly dissimilar to the third person. So you have the prime focus image, you have similar, that is a positive image, and you have dissimilar image, which is a negative image. You train a model to find out the relevance or similarity or the distance, typically the Euclidean distance, between the first two, xi and xj. The distance has to be closer and closer, and the distance between xi and xk has to be bigger and bigger because that person is supposed to be dissimilar. And the model can eventually figure out. And next time you give the picture of a human being the model has never seen, it first runs an algorithm just to pick the xj and xk pictures, and it has to be an intelligent model, because if you pick completely random two images and they are no way related to this model, the model will fail. But there's some intelligence right there into that algorithm. But once you pick the xj and xk images, it will run a quick comparison, actually in this case a classification, and find out if xj is close enough to xi or not. And that's when you actually start comparing, okay, the person I saw at 9:30 a.m. on this part of the city on a Sunday is the same person I saw on the Tuesday evening at 6:30 p.m. That's what is. So this paper was published in April of last year. There's another paper which came. So you have just a basic softmax loss. There's softmax plus contrastive loss. That is, you pick two images which are distinctly different and then train a model based on that. That improved a little bit of accuracy, but I think triplet loss further improved. L softmax loss, it's a large softmax loss, so they actually found two images. Softmax loss is only just two images, one is right and the wrong. They trained the model between two images which are really, really apart. There's another model called center plus softmax loss. That seems to be the really good one, but then sphere phase is in detail explained in this model, which actually has shown really good results. I don't have time anymore. I have a couple of others. In this case, the paper talks about analyzing videos. In the previous examples, we talked about individual frames, that is, images being processed to identify who the person is. But if you have video, let's say there's an act of crime happening, or there's an accident that's happening, how would you know it's an accident? If you take an individual frame, maybe the car is just moving, two cars are coming just close to each other. But if you put all the frames put together, you know it's an accident. And then this model can tell you about that. I have 2 more minutes, but I have a couple of other slides. But if you have any questions, I'll be happy to answer.
There's another thing, detection, crime detection.
Yeah, crime detection, by the way, there are some models already available, even in certain cities in the US, which can detect gunfire. And it does not need any video, just an audio. So you can actually have sensors placed in strategic places in the sense a crime-prone area. And actually there's a company called Spot Detect, I guess is the name of the company. You can check on the website. They have a very nice GUI controlled system. You can actually see in the map of the city red dots where there's a gunfire that happened, including the timestamp of that. So crime detection, of course, is one. Videos are being used to detect, let's say, a theft. Let's say surveillance cameras would be constantly watching. If nothing is happening, it won't alert, but if there's a theft or an accident that's happening, it can actually alert the people. Yeah, there are a lot of solutions available for that too.
Basically, it would triangulate the location of the shot based on the placement of the speakers.
One is the location. I think it's not that a big issue because you have sensors located in many strategic places. It knows how far away. But detecting a sound of a gun in the context of so much of other noise, you actually have lots of noise. Detecting that, because if you run a model, it actually has to, there's something called PCA, Principal Component Analysis. You actually have a signal that's coming in and which is full of noise. You got to break the signals into multiple other signals, eliminate all the noise, and figure out whether this particular signal is a gunshot or maybe a toy gun, or maybe there was the flat tire. Suddenly the tire exploded and hence there was a. So you got to really figure out. You don't want to waste all the resources of your cops, even if it's a fake sound. So it's more of a sound issue than the location issue.
But there is another issue, the low quality, cheap sensors.
Yeah, the life of a sensor is an issue all the time, and I was talking about earlier too. If you have a smart city solution, you got to define the solution so that it's flexible in future too, because you have newer types of sensors being used, and then that's collecting data. I know the next. My time is over because I think the next presentation is coming up. Thank you guys. Thank you.
So we get the papers.
Yeah, you can take the picture. Oh, you want other slides too? Okay, this is large-scale geotagging. For example, if you have models which can figure out where there is an event happening, there's another paper. But I need to leave because I know the next speaker is ready. Thank you, guys.
Do you have a context slide?